Hello and welcome to our astrophysics course. In our first chapter, we will be presenting you with an introduction to the beautiful and interesting fields of astronomy and astrophysics, important definitions, and a brief overview of the history of astronomical discoveries in this course. First, it is important to note that astronomy and astrophysics are beautiful fields of study. We are constantly evolving our understanding of the universe. There is never a dull moment when discussing these fields. We can observe distant galaxies hundreds of miles away, capture pictures of Mars clear enough to see her enormous canyons, and remnants of a star which we saw explode in our night sky. We are able to see new stars and planets being formed in the Orion Nebula, 1400 light years or 1.34 times 10 to the 16th kilometers away. Our Hubble telescope is one of the many astronomical instruments in space. Outside of our atmosphere, it is able to capture crisper and clearer images than we had previously thought possible. In this vast universe, we call one planet home. Earth is humanity's home base. We are able to take pictures of ourselves, an astronomical selfie if you will, via some of the other astronomical instruments we have orbiting us. We can use data from Earth and from space to form a clear image of what we look like. Zooming out a bit further, we can see that we live in the Milky Way galaxy. Our sun is just one of billions in our galaxy. Since we are inside the Milky Way, what we see in our sky is a cross-section of the galaxy. We keep careful tabs on what we observe in our galaxy. This star cluster we've dubbed M9 contains roughly 250,000 stars. Our galaxy is not the only one visible to us. We are able to observe our neighbor, by astronomical standards, galaxies, like the Large and Small Magellanic Clouds. The Andromeda Galaxy is the closest spiral galaxy, like the Milky Way, to us. Close is measured by a different standard in astronomy. This galaxy is still 2.5 million light years from the Milky Way. Even farther, at 60 million light years away, we can see a cluster of galaxies. Each blob in this image contains billions of stars. Now, time on the cosmic scale is much different than we are used to. We can put this in perspective by scaling our universe's lifetime to a yearly calendar. In January, the Big Bang occurs and our universe is born. Fast forward to May, and our Milky Way galaxy is formed. All the way in the 9th month of this year forms our solar system. During this month, life forms on Earth. In October, our atmosphere becomes oxygenated. Already into November, the first complex life form begins to take form. It is not until December 25th of this year that dinosaurs appear. Just 6 days later, humans appear. We appear in the evening on the last day of this cosmic calendar. We are relatively brand new to our universe. The Big Bang occurred approximately 13.8 billion years ago. Now that we went over some of the amazing knowledge and images we have gained from this field, we need to discuss exactly what astronomy is. Astronomy refers to the study of the universe and all the objects and phenomena it is home to. From its original derivations, astronomy means laws of the stars. Very simply, we study stars, planets, and space. Astrophysics is a subfield of astronomy. It focuses on the interactions of objects in our universe using our known laws of physics and chemistry. We employ physics and chemistry to study the energy emitted by the objects of the universe. This energy exists in the electromagnetic spectrum. We study the properties such as luminosity, density, temperature, and chemical composition of space objects. Several branches of physics, including quantum mechanics, relativity, and particle physics, are used to learn about our universe. Another branch of astronomy is cosmology, a study of the origins and evolutions of our universe. It focuses on the origin, evolution, and future of our universe. Now, for a brief tour of this universe we call home. This tour was made possible by astronomy, astrophysics, and cosmology. First, we are able to see the Earth and the Moon drawn to scale. As you may notice, the Moon is a lot farther away than you may have realized. 30 Earths could fit between us and the Moon. Next, our planets to scale next to our Sun. As you can see, Earth is relatively small compared to the giants Jupiter and Saturn. Even those planets, though, are dwarfed in comparison to our Sun. It is worth noting how small Pluto is in comparison to our solar system. It is one of the reasons its title of planet was evoked. Astronomy has a long and interesting history. Since we have records of humans, we have records of their observations of the night sky. Without the light pollution we see today, ancients were able to see the stars that shine brightly in our night sky. They made observations of these stars, some based in religion and myth, but others still insightful and valuable observations. Between 13 and 20 billion years ago, at the center of our universe, the Big Bang occurred. The traveling that occurred between 30,000 and 6,000 BC means that it was very likely that ancients were using the sky to navigate these vast amounts of lands. In 3000 BC, Stonehenge was erected. They used this as a type of clock to tell of the solstice and lunar and solar eclipses. In 280 BC, Aristotle suggests that the Earth revolves around the Sun and makes the first estimation of the distance from the Earth to the Sun. In 240 BC, the first Earth-size estimation was made, and quite accurately so. We will learn more about how this was accomplished later on. In 45 BC, the introduction of the purely solar Julian calendar came to be. Andres Planetis published his rendition of the Ptolemaic system in 1661. The Earth, the center of the planetary system, is shown in great detail, with the North Pole in the center, America in the upper half, and Europe and Africa in the lower half. A silver chariot on the white and silver circle indicates the path of the moon, a golden chariot on a golden circle the path of the sun. The planets are found on the remaining circles. It shows the Earth as the center, as believed of the time period. The ecliptic model of the universe was how the planets and sun had to be modeled in order to explain the movements of them in the sky while keeping Earth as a stationary center. In 1054 AD, astronomers in China observed a supernova in Taurus. In 1120 AD Egypt, the first observatory in medical Islam was constructed. It was destroyed 5 years later. In Central Asia in 1420 AD, an observatory was built by Ulugh Beg, in which he catalogued over 1,000 stars, making him debatably the most important observational astronomer of the century. In 1543 AD, Copernicus publishes his heliocentric, or sun-centric, theory of the universe. Copernicus's theory highlights that the Earth is not the center of the universe, and that all spheres revolve around the sun as their midpoint. This makes the sun the center of the universe. Copernicus also theorizes that the sunrise is due to Earth's revolution around the sun, rather than the sun's revolution around us. His theory about the Earth not being the center of the solar system fixes many apparent inequalities they observed with the mindset of Earth as the center. His original heliocentric model is shown here. The more modern model is more clear. The sun is the center of our solar system, and the planets, including the Earth, revolve around it. In 1609 AD, Galileo turns his telescope to the sky for the first time. He discovers Jupiter's moons, our moon's craters, and the Milky Way galaxy in the heavens. In 1609 AD, Kepler's first and second laws of planetary motions were announced. He states that all planets move about the sun in elliptical orbits, having the sun as one of the foci, and a radius vector joining any planet to the sun sweeps out in equal areas in equal lengths of time. 1668 AD, Newton builds the first reflecting telescope, a telescope that uses mirrors instead of lenses. In 1675 AD, a Danish astronomer measures the speed of light. In 1687 AD, Newton initiates what we view as modern astronomy with his publications of his theory of universal gravitation. Here we can derive the time it takes for light to reach Earth by using known quantities of the time. Time is displacement, or change in distance over velocity. We know the distance from the sun to Earth and the speed of light. From this, we can find that the time it takes is 500 seconds, or 0.14 hours. It is approximately 8 minutes. In 1781 AD, Uranus is discovered by Herschel. In 1846 AD, Neptune is discovered, the last of what we now consider planets. In 1857 AD, the father of astronautics was born. His proposals were essential in our eventual flight to space. In 1905 AD, Newton introduces his special theory of relativity. In 1923, the Hubble telescope shows that galaxies exist outside of our Milky Way. In 1957, Sputnik, the first object to orbit the Earth, is launched by the Russians. In 1969, Armstrong and Aldrin step on the moon. In the following decades, we land on Mars, Saturn, and discover Uranus's rings and Charon. In 1994, we observe and capture comet Shoemaker-Levy crash into Jupiter. Our telescopes allow us to view the planets in wavelengths outside of our eyes' capabilities. In 1998, we begin the International Space Station. The next year, we discover the Hubble constant, a unit of measurement used to describe the expansion of our universe. In 2000, we find new evidence for water on Mars and create a detailed global map of Earth. Pluto has always been an oddball. Since its discovery, we noted that its orbit is off compared to the other planets. For part of its orbit, it actually moves closer to the Sun than Neptune. The final star for revoking its classification as a planet was when Eris was discovered. It was thought to have been more massive than Pluto, so wouldn't that make it a planet? Pluto is incredibly small compared to the other planets, so we had to create a clear definition of a planet in 2006. Pluto is considerably smaller than the other planets, does not tidy up its orbit as defined by a planet. So in 2006, Pluto lost its title of planet and was given the title of dwarf planet. In order to practice valid science, we must have a scientific method. This helps to ensure the validity of research. In broad, the scientific method begins with an observation. This observation leads to a theory, which leads to a prediction based on other predictions. The predictions are observed. If the observations agree, we can make more predictions. If they disagree, we must start over with a new theory. A more beginner scientific method can be outlined as such. We ask a question, do background research. We may even find that the question has been answered. If not, we need to educate ourselves on the circumstances and phenomena that concern our question. We then use this to construct a hypothesis. We test this hypothesis with an experiment and analyze the results. If the results only show that the hypothesis is partially true or false, we must create a new hypothesis and begin from that step. If the results provide evidence for our hypothesis, we report our results. An example of this is the moon's craters. The moon has craters. We can theorize the moon is made of Swiss cheese. We predict the moon to taste like cheese. We test this by sending astronauts to taste it. They find it tastes like rock. We re-theorize. The moon is rocky and the craters are caused by impacts. This is a bit of a non-serious example. Let's try another one. We observe a hole in our ozone layer. We theorize that the hole is growing due to CFCs. We predict a limit of CFCs will disappear this hole. We test this by limiting CFCs. The hole remains. We modify our theory. The hole actually oscillates in size, but CFCs did contribute. This is an example of a hypothesis only being partially true. In science, a theory is not just a theory. A theory is something that has stood the test of time and has not been proven false. In science, we cannot prove anything to be true, only false. A theory is more similar to a law than a hypothesis. We've tested a hypothesis again and again, over and over, and has not been proven false. We can infer that it is unlikely to be proven false with more testing. This makes it a theory rather than a hypothesis. In order to quantify things in science, we must use units. This table shows our commonly used units of mass, length, and time. We are used to feet, seconds, and pounds. It is important to note that pounds is actually a unit of weight, not mass. Weight can differ depending on gravity. Your weight will be different on the moon, because weight is a force equal to the mass times the acceleration due to gravity. Your mass is always the same, no matter where you are in the universe. An example of this is a 60-kilogram person. On Earth and the moon, this person has a mass of 60 kilograms. On Earth, though, our acceleration due to gravity is 9.8 meters per second squared, whereas it is 1.6 meters per second squared on the moon. This makes us have more weight on the Earth than the moon. A lot of the times, we are talking about very large or very small numbers in science. We do not want to have to list 9 zeros after a decimal point, so we use different notation. If something is incredibly small with 12 zeros after the decimal point and before the first significant figure, we use pico, or 1 times 10 to the negative 12th. If something is incredibly large, say with 12 digits after the significant figure, we use tera, or 1 times 10 to the positive 12th. This makes our math much cleaner and easier to follow. In astronomy, though, we are dealing with incredibly large numbers. For this reason, astronomers have their own units. A parsec is the distance at which one astronomical unit subtends an angle of 1 arcsecond. For light, this is 3.26 light years. This is not large enough for objects outside of our galaxy. We have to use kiloparsecs or megaparsecs to talk about these objects. And that wraps up our first chapter. Our next chapter will discuss the birth of astronomy and all the amazing discoveries that contribute to our large bank of knowledge today.